Hello, everyone. We're ready for the next session, which is on rheology at extremes. Before we start, Stella, who's been doing an amazing job of running this meeting, just put in the chat the survey. The survey is important for those of you who haven't filled it out because we need data, right? We're writing a proposal, and in order to make sure that proposal is as good as possible, we need data. And so if you guys could please fill out that survey, it'd be super helpful if you haven't done so already. And for those that have done it, many thanks. Okay, so let's get to the science. Our first talk is by Lowell Miyagi at the University of Utah, and it will be on in situ texture and stress characterization in earth materials. Reminder that if you have questions for Lowell, you can put them in the chat or raise your hand at the end of his talk. And with that, oh, great, your slides already up. Great, thanks, Lowell, go ahead.
Yep, thank you very much. I'm gonna focus a little more on sort of technique and what we can measure as opposed to Shun's sort of larger scale overview. But anyway, start off acknowledging that there's lots of people involved in this. And so this is, obviously not a one-person show. And actually, probably most of this was done by my students, and I'm just being a standard PI and acting like I did it all. So what I was going to talk about today is understanding texture and how we can look at stresses. And Shun did a really good introduction to this. And so I just thought I'd start here, where just showing locations in the earth where we observe seismic anisotropy. And it's widely believed that in many of these regions, or most of them, anisotropy, at least at depth, is likely to do to texture or crystallographic preferred orientation. And so that's kind of the motivation for studying this characteristics of rocks. So the way we go about measuring this is we use a technique called radial diffraction. And so we bring our X-ray in from the side. This is an example for a diamond anvil cell, but it works in principle for really many devices like the deformation dia or the rotational Drickemer. And we collect our diffraction on a some kind of detector. And the idea here is that because our beam is perpendicular to the load axis, we sample lattice planes at many orientations to compression. And there are kind of two phenomena that we observe. One is as we compress our sample, these normally circular diffraction rings distort into ellipses, and the variation in lattice spacing on each peak tells us something about the strain on that particular lattice plane. The other thing we'll observe is as we deform our samples, we'll develop systematic intensity variations around the diffraction rings, and that will tell us something about texture or crystal preferred orientation. So we then process this using a full pattern Rupelt refinement. And so, for example, here we take our raw diffraction image, we unroll it, and this is our data here. And you see these variations in peak position as a function of azimuth. The compression direction is here. And we also see intensity variations along here. This is a sample of bridgemanite. If people are interested, we have some tutorials on this particular software and how to use it. So anyway, what we do with this information is, I think many people know this, but it's probably worth running through, is we represent texture in a few ways. One of these is an inverse pole figure. And for the type of work I do, we're typically doing compression experiments. And so I show inverse pole figures of the compression direction. And what this does is it shows us one sample direction and many crystallographic direction. And so one way we can understand that is we can look at this diffraction image here. Again, this is our compression direction. And if we look at our 002 peak, we see that it's brighter in compression. And so if we want to indicate that there are more orientations there, we can plot, say, for example, hot colors here at the corresponding orientation in the inverse pole figure. And then if you look at like 020, you have a minimum, so you can plot a cool color. And you can basically do this for every peak that you sample. And you also have some constraints from crystallography, so you know where orientations you don't sample are. And so the idea here, we'll plot these in multiples of random distribution. So if it's one, that means it has the sort of distribution we expect for a random. And if it's 2 times or an MRD of 2, that means twice as many orientations as we expect. We can alternately, right, use a pole figure. And so, for example, here, if we had a population of crystallites and we plot the poles to these planes here, we can plot where they would intersect on a sphere. And now I'm going to turn it sideways and I'm going to look down from the top, and we can sort of contour our orientations. And for example, this would now show us the whole range of sample orientations, but just one crystallographic direction. So that's sort of two ways to look at it. And these are, of course, interrelated. So for example, here I have a compression experiment. This is on Periclase. And what we see here is compression is in the center. Our 200 pole figure shows a maximum in compression. And indeed, if we look at the inverse pole figure, we see a maximum here in the corresponding orientation. And 111 and 220 have minima, which we see over here. Okay, so I know I'm in a sort of rheology at extreme conditions. Yanbin mentioned that it might be of interest to see some things at lower pressure. And since I've done some work in that area, I thought I would throw in a few slides about this. So one thing we could do is we could do sort of the lowest pressure, which is ambient, and we could look at an application to crustal anisotropy. So here we are looking at shales. Shales are ubiquitous sedimentary rock, and they're really important for seismic prospecting. They tend to have very strong anisotropy, and as it turns out, a large percentage of sort of missed boreholes are due to improperly accounting for anisotropy when prospecting for oil-rich deposits, right? So one thing you can do, this is at Argonne, this is sector 11. This is a high energy beam line, so it's 115 kV. And what we can do is we can put our sample here on this goniometer. We can get up to about a centimeter thickness, but you have a trade-off between beam broadening and sort of how well you can resolve your peaks, or peak broadening and how well you can resolve them. And so what we do a couple things to increase grain statistics. One is we scan the sample in the beam while we're collecting diffraction. And we can also do some rotations to bring more samples into diffraction condition, and to also increase the resolution of our texture measurement. So we get something like 200 cubic millimeters of volume. So these are obviously complicated samples. This is an example of the Bakken Shale, this really famous one from North Dakota. This was a master thesis I helped advise when I was at Montana State. And you can see this is very complicated. It's got really low symmetry phases. It has a lot of them. Nonetheless, you can get a very good fit to your data. So for example, this is fit, or this is data on the bottom and this is fit on the top. You see strongly oriented clay peaks. And you can look at different clay phases. You can look at carbonate phases. This is an example of a Mancos shale that's in Utah. This is a master's student of mine. And so for example, the Mancos has much weaker textures in the Bakken, where the Bakken has about 13 MRD, the Mancos is about 3.5. You can then do something with this that's sort of more useful than just measuring the textures. You can take your elastic constants and combine those with texture for all the information for all the phases in here. And you can calculate something like P-wave anisotropy. So this is just a compilation of some data from a few studies that have done this. And what's interesting, much more than say compaction, if you look at just clay content versus P-wave anisotropy, you can fit almost a straight line to it. And it actually turns out that it seems like most of this anisotropy develops during deposition, and there's some studies on unlithified sediments from Death Valley that show that you have very, very strong textures prior to lithification and compaction. Okay, so you could then, if you wanted to move up in pressure a little bit, you could turn to something like the deformation dia. I know this was talked about, Yanbin talked about this yesterday for a bit. Obviously this was made to generate high pressures. So if you're a really crazy person, you decide, well, I'd like to try and do something at low pressure with this. And so you go through some extreme contortions to try and generate controllable lower pressures. And so this is what we did with this to try and understand deformation of shales. So we wanted something like 100 MPa and 100 C to be appropriate conditions for deep shales. And what we ended up doing was using a large sample assembly. So this is a 16 millimeter cube, and it's made out of this material PEEK, so this thermoplastic. And then this is showing our shale sample in there. So you can do a couple of things. So this is an example of one sample we got. This is given to us by Chevron. And so here we're actually putting it into extension, and you can see it start to fracture. You can look at textures in this case, because it's failing in a brittle way, you don't see much in the way of texture evolution. Sort of ironically enough, this turned out not really to be a shale, but to be a micrite. It's mostly calcite. So sometimes you get these samples from the oil companies, and they tell you it's one thing, and it turns out mineralogically it's something totally different. But we do have some shales here. We put, this is just showing full figures for one of the clays. We actually put our sample in with the foliation along with compression. That was entirely by accident. But now here, our 100 plane, which is the foliation of the clay, is oriented this way, and you can see that the maxima is basically perpendicular to our compression in the middle. This is sort of the start of compression, and this is at the end. And what you see is we start to reorient the clay. So we actually had basically just ductile deformation here. But the point is, you can use this sort of technique to track even these sort of complex low pressure crustal phases. Okay, so what I really wanted to get into here was application to the Earth's interior, and particularly into the lower mantle. And as Shun pointed out, there's some real challenges to this. We need to deform things at sort of 100 GPa and several thousand Kelvin. And there's also a challenge that many of these phases are unquenchable, right? So some are unquenchable, some are unstable, but this really necessitates the synchrotron and in situ studying of these materials in that fashion. So our goal here really is to understand the deformation mechanisms at high pressure and temperature in order to be able to understand how anisotropy develops in the Earth's interior. Okay, so to do that, we're not just collecting texture data. We actually need to go a little bit deeper, and to do that, we combine plasticity modeling with our experiments. So the approach that we've traditionally taken is to do a self-consistent model. And so in the self-consistent model, what you do is you treat each grain as an inclusion in a homogeneous anisotropic matrix. You incrementally strain that grain, and you do this iteratively for each grain. If you, for example, have 2,000 grains in your simulation, you strain each grain, you then average them to get your matrix property, and you do this iteratively until you reach the total strain you want. Now, there's been sort of two approaches to this. One is the viscoplastic self-consistent method of Liebmanson and Tomei. And so here, this is a rate-sensitive plasticity code. And what you do is you favor different slip systems in your structure, and it will, as you strain it, will develop texture. And you can see that for different slip systems, you get characteristic texture types. And so you can match those to your experiments, and you can infer what slip systems are active. But this model doesn't know anything about elastic deformation. It completely neglects it. On the other hand is this elastoplastic self-consistent code. So this allows you to look at things like lattice strains, or these QHKL, as a function of the plane and how much strain is on each plane. And it turns out that favoring different deformation mechanisms gives you different lattice strain anisotropies. This is an example from Merkel et al. On HCP cobalt. However, this is not a rate-sensitive plasticity code, and so there's some issues with modeling rate-sensitive minerals, and also for doing really large strain simulations. So in 2010, Wang et al., he was a researcher at Los Alamos working with Carlos Tomei, formulated this elastoviscoplastic self-consistent code, which is a fully integrated code using basically both of these approaches simultaneously. So it's fully rate sensitive, it tracks elasticity and plasticity. I had a student who in 2017 applied this to high pressure, and this was a collaboration with Sebastian Merkel and Nadej Hilaret at University of Lille. And one of the adaptations we had to do was to put in equations of state and pressure dependence of critical resolved shear stresses and pressure dependence of the elastic properties. Okay, so this is just showing an example of this. This was Pericles. This is one of my former students, Jeff Gay, being facetiously excited about beam time. And this is Feng here trying not to smile. I'm very deadpan. So what we did was we took an MgO sample, we strained it at 3 different strain rates. And then what you get is you get a pressure versus strain curve. And what you want to do with that, because we can measure with radiography, we can measure the length of the sample. We know what epsilon 3,3 is, but we don't actually know what epsilon 1,1 and 2,2 are doing. But if we match the pressure curve, we can constrain what those other principal strain directions are doing. So that's kind of the first step of the simulation, is matching the strain rate and then the pressure curve. Once you do that, then you can start playing with your critical resolve shear stresses and your slip system activities, and you can fit both your experimental lattice strains. So for example, here, the open symbols are the experiment, and the lines are the simulation from EVPSC. And over here are experiment textures, and then this is the EVPSC texture. And you can plot as a function of your axial strain. You can plot your slip system activities. And for example, in this particular experiment, we have dominant 110 and 100 slip, mostly 110. Okay, if you wanted to go to higher pressures, there's some limits in how high you can go with the D-dia. Here we've got some data from a resistively heated diamond anvil cell. These were done at Petra 3 at DAISY. And so there were a series of runs done compressing along various isotherms, so up to 1400 K. The temperatures correspond to where the bottom of the inverse pole figure is, and up to about 65, 70 GPa. So what we see here is, at room temperature, you have very different textures than at higher temperature. And so you can again do some EVPSC simulations for room temperature versus high temperature, and you can see the changes in slip system. So at 300 K in the diamond cell, 110 slip is nearly 100% accommodating deformation. But as you go to like 1400 K, you have a much closer mix of those two slip systems. So we actually revisited MGO and the D-dia again. And so here we did a range of temperatures and pressures. So here's like 1273. So that was the highest temperature we did. We did 2 and 7 GPa. Here's a 873, so this was the coolest temperature, and these were both about 3 GPa. And then we also did a 1073 K with 2.5 and 8.5 GPa. I think one thing that's interesting, at 1273, we basically don't see any lattice strain anisotropy. Everything falls essentially on the same line. There's a bit, you see more fluctuation in the lattice strains. Interestingly, when you go to this 1073, and 2.5 GPa, you can see that the order of the lattice strains has changed, has changed between 2.5 GPa and 8.5 GPa. And so there's some change in deformation mechanism occurring. You can also plot flow stress here. So if you wanted to look at the flow stress in GPa for these different runs, and you can see variations in strength with temperature and strain rate, for example. Okay, then what you can do is you can model all of these with EVPSC. Again, this is my student Feng Lin. This is is in prep and is a last chapter of his PhD thesis. So for example, here at 873, you get a pretty good match here. So this is actually primarily 100 slip. And then at looking at these two, 1073 and 2.5 and 8.5 GPa, you see a change in slip system. And again, you can match the lattice strains and the texture quite well. And this has over here, you have a mix of 100 and 110. And here you have some more 110 or 100, sorry. The highest temperature ones didn't develop texture, which we interpret that and the lack of lattice strain anisotropy to be indicative of diffusion creep. Okay, so here you can basically plot all these experiments where we observe texture and we simulate them, and you can model the slip system activities and look at them as a function of temperature and pressure. So for example, if we compare these two runs here, which were at a similar pressure, if we look at the change in slip system activity from 873 to 1073, we see that the 100 slip increases by about 5%. If you look at these two runs here, which are at the same temperature, but 2.5 GPa and 8.5 GPa, we see the increase in pressure increases the activity of the 110 slip by about 15%. So sort of another way to put it, this is obviously oversimplifying things, is that a pressure of 2 GPa has about an equal and opposite effect of about a 200 K temperature increase. You can also do things like look at multi-phase deformation. So this is another former student of mine, Samantha Cooper. She's now at Los Alamos National Lab. And so this was, again, this high temperature deformation in resistive heated DAC. This was done at Petra 3 in Hamburg. And so here are lattice strains for these bridgemanite and ferropericlase phases. And if we look at the textures here in bridgemanite, we see texture development there, but we don't see a lot in ferropericlase. So you can apply the same sort of approach here where we use EVPSC to model textures in the lattice strains. The lattice strains here are a bit more complicated to match, but if we get the ordering correct on the lattice strains, we find that to do that and to match our texture requires actually 2 slip systems. So slip on 100, but in 2 different directions. And you need close to sort of 50-50 deformation accommodated by those 2 slip planes. Now, one thing this model doesn't do, because it's a self-consistent code, each grain doesn't know what the other grain's doing. You can't account for microstructure with a self-consistent method. So what we did there, and really what we wanted to do is try and understand why the ferropericlase, which is the softer phase, was not generating texture, is we can go and do something like finite element simulation. Now, it turns out doing finite element simulations with low symmetry phases like bridgemanite, which is orthorhombic, you tend to run into problems because the high plastic anisotropy causes your finite element meshes to tangle, and then you can't solve your computation. So the approach we used here is this ALE 3D, which stands for arbitrary Lagrangian Eulerian 3D finite element, which was pioneered by Nathan Barton at Lawrence Livermore National Lab. And so what this does is it couples an advection step to your finite element code. So at sort of each incremental deformation, it allows your microstructure to advect and evolve, and then it remeshes your finite element. So it basically accounts for large strain microstructural evolution. So here we're only going to about 40% strain. This is a simulation here. The blue stuff is bridgemanite, and the more blue it is means the more internal strain in the grains, and the hot colors are your periclase, and sort of the more purple it is, the more internal strain it has. I should say this particular microstructure, we treated ferropericlase as an inclusion in bridgemanite, but we also tested ones with sort of equilibrium microstructures, varied grain size between the 2 phases. And what we see is when you have ferropericlase included in bridgemanite is you tend to weaken the texture in the ferropericlase. So just to note, these are on 2 different scales. So the bridgemanite texture is actually quite a bit stronger than first appears if you don't look at the scale bar. The other really interesting thing I think that you see here is if you notice, like particularly in the MGO phase, as a simulation runs, you can see higher strain regions developing inside each grain. Okay, so the strain is very heterogeneous within the grains. And this is true in bridgemanite as well. So I think this is one area where future upgrades where we have, brighter, smaller beams may allow us to interrogate strain on a sort of subgrain level to try and understand how these things are deforming at a finer scale than these sort of texture measurements are giving us. And people are already doing this with multigrain techniques. So finally, I thought I would just wrap up. Maybe I'm ahead of time here. With sort of some future work we're doing and that I think is relevant for upgrades here in the US. Again, this is at Petra 3 in Hamburg, and this is a collaboration with the Los Alamos Detonation Physics Group. And so what we're doing here is we're using a piezo-driven diamond anvil cell, and this has been done to study phase equilibria and rate sensitivity, sort of phase transformation kinetics. And what we've done here is something, in theory, not so difficult. We've basically made a side opening and we've turned our diamond cell sideways so we can do radial diffraction. And the nice thing about the DDAC is you can control your strain rates very well. So I think on one hand, this can potentially allow for controlled strain rate, slow strain deformation, but it also, coupled with extreme brightness and fast detectors, allows us to do high strain rate deformation. So this setup here, we have our X-ray detector. You've got the DDAC here with the X-ray coming in. Here's an optical microscope, and this is nice because we can see our sample and we can take a video of it in real time. So this was a sample of hafnium. So hafnium's here, and there's a little bit of copper pressure calibrant. And so we can watch it and we can map the strain in our sample during the deformation. Now, when we go to high strain rates, what's really neat about the DDAC is this puts us really in the strain rate gap between these static sort of LVP diamond cell techniques that are these slower strain rates, and the gap between that and things like gas gun and laser shock compression. So while there is the Kolsky bar in here, in these sorts of strain rates that you can get with the dynamic diamond amble cell, this is not really amenable to putting on a beamline and doing in situ capabilities like you can with the DDAC, which is really quite easy. But the point I wanted to make is that this gap in strain rates is actually where the majority of strain happens during an impactor. And so this is a really nice tool to study deformation mechanisms during impacts. And this is going to be the PhD project of my student Chantel. And right now what she's working on is zircon, which is commonly an accessory mineral and was found in meteor impacts. And people had discussed using the zircon to readite transformation as like a paleopiezometer to tell something about impact conditions. But if we look at this phase diagram, the dark black symbols here are where the phase boundary is based on static compression experiments. And over here is where they're observed during shock compression experiments. And so there is a rate sensitivity to the phase transformation. And there also appears to be in the literature conflicting reports on the deformation mechanisms of zircon between static and shock compression experiments. And so what she's doing is looking at zircon and trying to explore a range of compression rates to understand what the deformation mechanisms of zircon and where that phase transition occurs. Okay, with that, I'll wrap it up. These are really general conclusions. There's a lot of applications for texture and lattice strain analysis that can range from sort of bulk anisotropy measurements to rheological experiments. And then just sort of as we go into the future, looking at higher strain rate, time resolved measurements, and then also being able to interrogate samples on a sort of finer scale. And with that, I'll stop and take questions.
Thanks, Lowell. That was great. Questions? Yes, Sean Corrado.
Yeah, very interesting results. When you say slow deformation, what kind of strain rate?
Oh, what's the lower limit of the DDAC? Is that what you're asking?
When you show the results from fast strain rate and slow.
Oh, yeah, I would have to look. So this was actually done in a membrane because we haven't had access to Petra. So the faster strain rate here was actually only like 10 to the -1.
Okay.
Something like that. And the slower one was maybe an order of magnitude slower. So we're hoping to go like 2 orders of magnitude faster than that. We have a beam time in DAISY beginning of October, which hopefully we won't get locked out by the EU.
Yeah, so, and then when you say deformation, is that a uniaxial compression or?
Yeah, this is in uniaxial compression. You could do it hydrostatically. Here we're doing these experiments non-hydrostatically. That's correct.
Because your results are very interesting. And I was trying to compare with our results, like a weak phase MGO, as I showed you. In our case, it's a rotation shear, simple shear. And the MGO is very elongated, but in your simulation, it is not.
Oh, are you talking about something like here?
Oh, yeah.
Yeah, and I would guess this is partly geometry. So this is a confined axial compression, right? Yeah. So we can change the boundary conditions, and this is also only about 40% strain, right? So we're trying to mimic what we can achieve in the diamond amble cell.
Okay.
So you can kind of get a hint here where you see some of these things starting to elongate. They're not quite interconnecting, but you start to see this. So So I think potentially you can do a larger strain, right? It's computationally expensive to do a larger strain, right? This has to be done on Livermore supercomputers for a couple of reasons. One, you need the computing power, and two, it's an export controlled code, so it has to be run on their computers. So there's some sort of logistical issues to it. But in theory, you know, they use it for things like ballistic impacts, where things are strained to extremely large strain rates, and they're interested in what the microstructure does then. I would say if you want to look at something, you know, like what would happen, say, during mantle convection, Ricardo Liebenson at Los Alamos has an fast Fourier transform plasticity code that's coupled to an advection code, and you can do large strain. So he can make like myelinites. So he's done some simulation on deformation of granites, for example, and formation of myelinites. So you can do large strain microstructure like that. It's computationally faster, but it doesn't have quite the same sort of microstructural resolution as an FDM code.
Okay, thank you. Yeah.
Thanks, Lowell. I think we're out of time. If anybody else has questions, please type them in the chat and he can answer them. That finite element modeling is really cool. I really enjoyed that.